If you enjoy Astronomy FM radio, please let us know with a small donation. We do rely on your support, and it's true. Every little bit counts.
AFM. You're listening to AFM radio on astronomy.fm, around the world and beyond.
Coming up next, it's time for an AFM radio original program, Space Pirate Radio, brought to you by the voice of astronomy, matey. This is astronomy.fm.
The pirates are coming. The pirates are coming. The pirates are coming. You better...
Arr! Arr! All right, good one. Welcome everyone to Space Pirate Radio, Wednesday evening, June the 12th, 2019, about 9 o'clock in the evening for those of us here in the eastern portion of North America. Universal Time, we put that at 1 o'clock in the morning, June the 13th, Thursday morning, again, of course, 2019. Broadcasting live for the next hour. Our co-captain Diane is out of town this week. We do have a special guest back again, Jerry Hubbell from Explore Scientific. Hey, Jerry, how you doing?
I'm doing awesome. I appreciate the invite. I think the last time we were on, I think I was on with Scott Roberts, my boss, back in January.
That's true. Yep. Oh, forgot to mention, of course, everybody, come on over to our astronomy.fm chat room if you want to chat amongst everybody in the chat room and send messages to us. Feel free to do that during our live presentation right now. Well, you've been doing some interesting stuff with the Mark Slade Remote Observatory.
Yeah, so that's right. We have been working on a fairly long-term project dealing with exoplanets. I don't know if did we talk about that last time? We may have talked some about it.
I don't remember. Let's do it again.
We can always talk about exoplanets. They're fun.
Sure.
So I guess when we talked about coming on this time, I wanted to share some of the things I've been doing to share the work that we're doing at the MSRO and specifically about the exoplanets work that we're doing. I gave a talk at the Northeastern Astro Imaging Conference in Suffern, New York in April. I was invited there to give a talk about the instrument that I've been working on the last year. It's kind of interesting. It basically enables the amateur backyard astronomer to do more effective work, to do measurements on exoplanet transits.
Go ahead.
So I gave that presentation, had a lot of interest, and people are really interested in doing this for themselves. I think that's why we started. But I discovered a paper last year from the University of Pennsylvania. I think, Penn State University is what it is, and they've been working on this instrument for professional telescope systems. It's called a diffuser, and what it does is it spreads the light out to be able to get more precise measurements when you're measuring the light dip for the exoplanet. And this new diffuser is a little different than the standard method, which is to defocus the image on the CCD of the star to gather more photons. Basically, the goal is to gather as many photons as you can get, and we're talking about millions of photons for every exposure. Mm-hmm. And you do that to be able to increase the shot noise precision. I'm not sure everybody may be familiar with what shot noise is.
Yep. We've got very beginners here too, so let's explain everything to them.
Okay. So to start out, in order to measure a small dip that we're talking about a 1% change in the light or less, okay, typically. And that's that's typically the precision that standard measurements are done with asteroids and with variable stars. You like to get a precision of around 1%, and that's a very good to excellent measurement. But we're talking about going 10 times better than that if we can get away with it. So we're trying to get 10 times better than the standard very good to excellent measurement on a star, because exoplanets, the light dip is only 1%. So in order to measure that accurately, you have to be 5 to 10 times better than that. So we're talking about measurements down to 0.2%, okay, which is 2 millimags. So a millimag, or 1% is equal to 10 millimags as far as the change. And we're talking about measurements down to 2 millimags or so. So that's what we're faced with, trying to do that measurement. There's two sources of error when you do that. Okay, there's the shot noise, which I mentioned a minute ago.
Somebody asked, could you spell that?
Shot noise.
S-H-O-T or S-H-O?
S-H-O-T.
Gotcha.
It's also called Poisson noise, which is a French guy that discovered it, I guess, back in the 1700s or 1800s, maybe. I don't remember exactly, but it's called Poisson noise. All right, that's a French name. And basically, it's a statistical noise based on, so everybody's familiar with what light is. It's photons. And photons as a source of radiation is a random process, okay? So when you collect these photons on a CCD imager, they come in at a random interval, okay? At a certain rate, average rate, okay? Now, so the more photons you collect total, the more precise the value is for that time. So let's say you collect 1 million photons in a minute, okay, on your CCD. The error in that, or the precision of that number, is equal to the square root of the total number of photons. Okay, so in that regard, 1 million photons, the square root of that is 1,000. Okay, so the precision is equal to 1 over 1,000. Okay, or the signal to noise ratio, you can consider it that way, is equal to 1,000. Now, if you were to collect 10 million photons, okay, the precision would increase. Your signal to noise ratio would increase to around 3,300 versus 1,000, because when you take the square root of 10 million, now it's a lot higher precision, because you're accumulating these photons, right? It's like a bucket that you're filling up with photons, and so the level that you're measuring it to, it's like measuring the water level. Okay, the more water you have in a column, the more precise the measurement, because the column's much higher. So
10% of a bucket is
a relative measurement depending on the total signal. So that's what the shot noise precision increases. It's a statistical thing, and so the more photons you collect, the better the average value. Basically, is what it comes down to.
As I say, with water, 10
more precise.
With water, 10% of a bucket is easier to measure than 10% of a thimble.
Exactly. So that's shot noise. That's one portion of the error.
Especially when you've got a dip in the light that is like right in the edge of that error margin.
So when you're doing that measurement, shot noise is one part of the error. The other piece is related to your sky conditions, and it's called scintillation. And everybody that's done imaging is familiar with seeing and scintillation. It's what It's what makes this, when the sky has got bad seeing, that's when you see that stars are twinkling. In the wintertime, especially when the air is really, the wintertime is really the worst time to do imaging because the scintillation is worse than in the summertime. Because you got temperatures changing a lot more drastic in the atmosphere, and it's really dry. You don't have all that mass of water like you have in the summertime when it's humid to stabilize the temperature. So that's why the wintertime sky is a lot worse in scintillation and twinkling. So the twinkling is a big source of error also. So you got the noise due to the twinkling. That's scintillation, and then you've got I call that short-term scintillation. And then you've got the long-term scintillation, which is really more related to transparency, where you have high clouds coming across your image as your imaging session progresses. So if you're taking 1-minute images and over a few hours, then from image to image you'll see small changes due to transparency changes, and then it's really noticeable. Like this hour, the first hour was good, and then the second hour might be worse. And you'll see, if you look at your images between the first hour and the second hour, you'll see a big difference compared to the minute by minute changes. So that's the long-term scintillation that you have to deal with, the noise. And there's no way around that pretty much. So the defocus method is designed to do the same thing that the diffuser does, where it spreads the light out. So when you defocus your star image on your CCD, it'll spread the light out and allow you to collect more photons without overexposing the star. So when you overexpose the star, basically you fill up the pixel. It's like filling up a bucket of water, and then you can't collect any more than that. So then it becomes overexposed. You don't want to do that when you're collecting photons. You don't want to overfill your bucket. So when you spread the light out, or more pixels, you basically have more buckets to collect the water and do the measurement more accurately. And so that's what you do when you spread the light out. You basically allow you to take a longer exposure to collect more photons. And the defocus method does that, and the diffuser method does that. But the defocus method doesn't do anything for the scintillation, the short-term scintillation. So when you're looking at the image, from image to image, you'll see the light move around, okay, to different pixels. All right, for each image, it'll look like it'll just jump around. The peaks won't be the same place. You'll have more photons in one pixel than another, and then it'll move around. Then the next exposure, it'll be a different pixel. Even when you calibrate the image, which means you're normalizing all the pixels to respond the same way to the same number of photons, the scintillation causes you to collect more photons in one pixel than another, and the calibration is not perfect. You still have small differences in the response of the pixel. That small difference between having a peak, having a bunch of photons collect in one pixel compared to the other, causes noise. Okay, I don't know if that's clear enough for everybody to understand. Basically, after you calibrate an image, you still have a small amount of error in the calibration, which is noise. Okay, that's the noise that I call it residual calibration error. And when your light signal jumps around between the different pixels, that noise gets induced into the value, right? Because you'll have a bunch of photons in this pixel, and then you'll have a bunch of photons in the other pixel, and the numbers are different. Even if the number of photons were identical, the value out of the pixel would be different. And that's where the number changes, and that's where the noise comes from. All right. So on the diffuser method, you have the same spread out pixels to be able to collect more photons, but the diffuser basically
kind of diffuses
out. It diffuses out the light, right? So it's spread evenly across the pixels. So any change in any one spot, it gets distributed amongst all the pixels. So it's like an averager, okay, in that regard. It averages the light out, and it makes it's a flat top profile. It's like a top hat shape. It's like almost like a square wave shape on the profile versus a bell-shaped curve that you get with a normal star image that's that you take.
Yeah.
So the fact that the diffuser averages out the light across all the pixels removes that source of error in the short-term scintillation. Does that sound pretty clear?
Yep, I got it.
All right, so now you've corrected two things with the diffuser. You've collected enough photons to get the signal-to-noise ratio very high, and that increases the precision down to below the 1 millimag that we talked about, or the 0.1% light. And then now you've taken each image and you've been able to reduce the residual calibration error down way below, or down to that same level. So now you've got the precision down from 1% down to, let's say, 0.5% or a little less. So that's key. Mm-hmm. The last thing you have is a long-term scintillation, and there's really no way to fix that. But what I found doing this work is that a lot, our backyard where we have our observatory, even with the moon out and the background, the sky background, as long as it's fairly transparent, the sky background could be fairly bright and the moon could be out, yet the transparency is smooth, and you got very little changes over the session that are easy to correct, basically. Mm-hmm. That cause small changes, and at that level it's around 1 to 2 millimag also. So being able to get the other sources of noise down to a certain level has allowed us to understand what the real long-term scintillation value is, where before it was masked. Okay, so when you don't have that stuff, when you don't have a correction for the short-term scintillation, and you don't collect enough photons to get your noise level down, all the noise is mixed up. Basically you can get just 1% precision. Mm-hmm. So you don't know what the long-term scintillation is, because it's buried in there. Okay, it's not measurable at that point.
Right.
So we didn't understand in the backyards of people's, in suburban areas or urban, or rural areas, that the long-term scintillation really is pretty low. And once you've removed these other sources of error, then you become scintillation limited. Basically, you've removed the shot noise error, you've removed the short-term scintillation, and now you're just long-term scintillation is a big part of your error, and we've discovered that it's very low value.
Okay.
So at that point, it allows us to increase the overall total precision of our measurement for the exoplanets.
I was going to ask you on the old method of defocusing, which if you have Cassegrain or reflector, you get a donut shape.
Right. So at the MSRO, we have a refractor, and the other testing we've done is with the Schmidt-Cassegrain telescope, and the central obstruction doesn't allow the diffuser to form a perfect top hat shape, and there's some diffraction. There's a little bit of diffraction around that central obstruction that causes a little bit more noise. It's not significant. It's noticeable, but it's not a big deal, I don't think. Okay. We need to do some further work on that, but refractors are definitely a little bit better in that regard, because a refractor, forms a whole circle of light, right?
Right.
When you fuse it, or when you defocus it, even, it looks like it's just a standard bell-shaped curve. There's no donut shape when you defocus it, right? So there's no way the light can be, or that diffraction for the central obstruction can interfere with the flatness or the measurement of the light, where it does a little bit with the diffuser compared to the refractor.
Do you use the diffuser right at focus, or do you defocus a little bit with the diffuser too?
No, that's the interesting thing. People, when you look at the diffused image, it looks like a defocused star. When you just look at the image, it's just a blobby star, right? But the profile shape is significantly different. So the neat thing about the diffuser is that you can focus a normal, let's say you're using a V-band as a reference filter, or even just clear, if you don't have any filter, and you do a focus and you focus the image to make a standard nice star field image. You can move the diffuser in front of the, move that filter into position, and it diffuses the star perfectly.
Okay.
And it's very insensitive, really, to the focus position. So you could focus it with the V-band filter. You could focus it with a luminance filter, and then move that filter out of the way and put the diffuser in place, and it's still the profile. The full width at half maximum, or the point spread function, is always the same. It's the same size, because it's really based on the design of the diffuser as far as the divergence angle and the distance between the diffuser and your CCD chip. That's what determines the geometry of the profile.
Yeah, that's what I was wondering too. Is your diffuser at focus, in front of focus, or behind focus? And does in front of or behind focus make a difference?
And I'm not sure what you mean. And the filter is in front of the CCD chip, and the CCD chip position can be behind focus or in front of the focus, and it wouldn't make a difference.
Okay.
Is that what you're talking about when you move the focus position, that it's in or out focus?
Yeah, well, yeah. I was thinking out of focus, your diffuser can be either in front of focus or behind focus, or if it was, in the focal plane, it would be like right at the focus point for the diffuser.
Well, the diffuser is a filter. Remember, it's not.
Right.
It's not in the focal plane. It's in front of the focal plane by about 30 millimeters.
Okay, that's what I was wondering.
All right, so it's like a filter,
right,
in that regard.
Okay, so your filter would be in front of focus, and your CCD would be right at the original focus point?
Right.
Okay.
Or it could be slightly in or out of focus. The CCD plane can be in or out of focus, and it wouldn't matter as far as the diffuser goes. Okay.
Gotcha. That's what I was trying to figure out, if there was any differences on.
No, it's very tolerant. In fact, we did that. That's the first test we did when we got the diffuser, was we tested how tolerant, or what the sensitivity to focus position the profile was, and the profile stays pretty much the same, even within. I think we moved it a couple of hundred steps, which is equal to about almost a millimeter in and out of focus. Okay. And it stayed the same.
Okay. Because I was thinking, let's see what I was thinking. Well, if your filter is in front of focus, it's going to diffuse the light. But basically,
it's going
to diffuse it out of focus. Yeah.
Right. There's a diagram of it. I think looks like Plaid Joan posted a link on the chat to the paper. There's a picture in there that shows the I believe that shows the configuration of the cone as it comes in. The light cone comes in through the diffuser into the CCD.
Okay, the link didn't go for me. How about anybody else out there? Not getting those links to work. Okay. All right, so we'll see if we.
Oh, it should be archive, arxiv.org. That's what the difference is. So let me type that in here.
Okay. We'll check that and see if that one works. All right, so just remind everybody that if you just tuned in, we're talking with Jerry Hubbell from Explore Scientific about doing some basically light sensitive test on stars to determine over long-term observation to determine if there's any transiting planets going in front of those stars. We're talking about using a diffuser to basically extend the size of the star, balance out the light, make it a little bit easier to measure than a point source.
Right, and it gathers a lot more data. It's a lot more photons to make a more precise measurement. That's the main key. And the other key to the diffuser is that it stabilizes the image. I mean, it's rock solid. If you were to look over a few hour period at the diffused image of the star,
mm-hmm.
You know how if you were to record that like a movie on a standard, even with the defocus image, and you would see the starlight move around, right?
Yep.
You would see the little star move, and scintillation would cause it to move around on the CCD.
Yep.
And you'd see that over time. When you're looking at the diffused profile image of the star, it's just there. It doesn't move. It's pretty amazing to watch, to look at over time, to see that it's just solid as a rock. It doesn't waver, doesn't do anything. It's pretty cool to watch.
Doesn't bounce around.
That's really why it works.
Of course, all assuming that your drive is working properly.
Right.
Keeping it centered.
Well, that's that's a key thing too. So one of the requirements when you're doing this, the traditional or standard requirements to do exoplanet imaging is you've got to have very precise tracking,
mm-hmm.
which means you typically use an auto guider to get a lock on a star over a several hour period to make sure that the light from your star on the image does not move, does not deviate from the few pixels that it's on. Okay. And this talks to the residual calibration error. So you don't want the star measurement to be moving on a group of 20 pixels here, and then it moves over to another 20 pixels, 10 pixels over, and then it comes back and then goes back the other way.
Mm-hmm.
You want to be able to keep the light on the same pixels all the time to minimize the effect of that residual calibration error.
Gotcha.
But
so periodic error is not good. Periodic error is not good.
Right. Periodic error is not good, and declination drift is not good in that standard scenario.
Gotcha.
So in that regard, it's a little expensive in skills and knowledge and equipment to be able to do this work with the standard defocus method. Okay.
Mm-hmm.
My contention, and we verified this with the measurements we've done with the diffuser, since it does stabilize the image and minimizes the effect of this residual calibration error because you've got such a big profile, it averages away the residual calibration error, that you can tolerate some drift in the image. And in the paper I talk about that impact. So that was part of the study, was to determine what difference it made when the declination, there was some declination drift. And one of the tests, we did this on 3 or 4 of our sessions. We allowed the image to drift like 100 to 150 arc seconds during the 3 or 4 hour period, both in RA and DEC. Okay. And RA, we don't have an auto guiding system in the MSRO main scope. We use a system. It's a high resolution encoder drive correction system called the Telescope Drive Master that doesn't correct, doesn't look at the sky to correct for the tracking rate. So you'll have whatever residual declination drift there is.
Mm-hmm.
If you don't have a perfect you don't have a perfect polar alignment, and you'll also have a little bit of RA drift if you're down, where the refractive error starts to make your star trail in RA and right ascension. So those two factors were involved with our measurement. So we were able to demonstrate with the diffuser that change in residual calibration error when it was tracking did not impact the noise in the signal, because it corrected for that, or it minimized that problem. Even when it tracked 100 and some arc seconds across this 3 or 4 hour period, it didn't make a hill of beans difference.
Okay.
So that was kind of cool to see. And that's part of in the original paper, they talk about that, one of the major features or benefits of using the diffuser. And that's one of the things I wanted to test for. So that means that anybody that has a decent system with a decent camera, they may not have perfect tracking. They may not have perfect auto guiding, but the impact of this drift on the CCD will be minimized if you use a diffuser versus using the standard defocus method.
Okay. Now, when you're doing, you said like 3 or 4 hours of observation. Is that you're building light over that period of time on the chip, like basically like the old cell camera stuff? Like you've got it on B setting, you're holding it open, or is it more like video where you're stacking images, or what I'm saying? Using a lot of short exposures, or you're using one long
3 minute exposures.
Okay. So for over 3 or 4 hours, you're using short exposures, a minute or 30-second exposures, and then combining them together. Does that sound about right?
This one's a sample.
Okay.
Can you hear me?
Well, yep, you're breaking up a little bit, but I got you.
Okay, you got me back now?
Yep.
Okay, so basically,
got your
samples. Each one of the winners, you do a frame, and then you over time for this 3 or 4 hour session. That's how it's done. Marty?
Yeah, I got you. Yeah, I was having you break it up there quite a bit, so can't tell if it's on your end or my end. Let me do they said it was you breaking up a little bit, so.
Okay.
Let me do a little station identification. Why don't you check your mic connection, stuff like that, and then we'll get right back. You're listening to... Go ahead.
Can I log back in? I'm sorry.
Nope. Can you stay in and just check your mic connection, stuff like that? It's not the mic. Our radio director says so. All right. So maybe it's just signal or something. All right.
Okay.
Let me do a little station identification and get right back to everybody. So listen in there. You're listening to Space Pirate Radio here on astronomy.fm. It is another Wednesday evening, and this one is June the 12th, 2019, about 9:30 in the evening for those of us here in the eastern portion of North America, also known as 1:30 in the morning, Thursday morning, June the 13th. So you're listening to us live. Got about another half hour of programming to go. Our guest tonight is Jerry Hubbell from Explore Scientific. And don't forget, we've got our chat room open. So if you want to ask Jerry some questions, come on and type in the chat room and log in here. So far, we've got in the chat room, we've got me, we've got Glenn, Plaid Joan, Twist Edge, Aquafew, Jerry's here, Plaid Mac, Optronics, Wes, MCD, Plaid Sister, and we've had people come and go out of our chat, all in our chat room right now. Don't forget, we're going to repeat this program with more programming, usually like Astronomy Ireland and Naked Astronomers, coming up after Space Pirate Radio. So please stick around if you like to and listen to more programming. All right, let's see how you're doing, Jerry. Let's see how you're sounding.
All right, test. How does this sound? Is it
That sounds
okay?
real good. Yep, nice and steady now.
Okay.
Sounds
All
good.
right. Okay. So I guess we were just talking about the remind me again, Marty.
We're at the let's see the diffuser and let's see the focus position of the diffuser.
Right.
And tracking errors. I think that was it.
Tracking
Yeah,
error. That's
tracking
what we were
errors.
talking about, the tracking error.
Yeah.
So the diffuser can correct for, basically, bottom line is that the diffuser can correct for any drift in the image across the CCD. And the main effect in the paper talks about is a residual calibration error that causes noise and that the diffuser can help mitigate.
All right. I think my question was, when you're doing imaging, are you doing like one long image, or if you're doing shorter images and then combining them together, or just using them separately and averaging the data out of them?
Oh, okay. So think about it this way. Each image, 1 minute or 3 minute image, is like a sample of the light for that time. Okay. And we plot that on the versus time. So it's a time series of data. And so what we're looking for the exoplanet transit measurement is a change in that value, right? From before the transit and after the transit to during the transit. So we basically have so think about before and after the transit, we've got a line, we've got a specific differential magnitude between. So we're comparing the target star or the exoplanet star to a comparison star that we assume to be fixed. Okay. So the fixed star, the difference between the fixed star and before the transit baseline is like a baseline value for difference. So let's say it's a 0.3 magnitude difference between the two stars. All right, so you draw a line on that baseline, and now we're watching for a dip below that line, and that's another line. So when it's transiting, it's going to be fairly flat, not perfectly flat, but but the total dip is going to be like a line below that.
Okay.
Okay, so you'll have a differential magnitude that's greater. Okay. Let's put it in that regard, in that relationship. So the plot looks like basically a U-shaped curve. Okay, you got a flat line, and it goes down, and then comes back up. And so when you draw those two lines, okay, so you got the baseline. You're averaging, basically taking all those samples and averaging them to draw that line across the top. And then when it goes down, it dips. You've got another line that you can use, that you can calculate, averaging all those samples when the transit is occurring, and that'll draw another line. And that's the magnitude of the dip, basically.
Okay, gotcha.
Now we're a little more sophisticated than that, where we actually plot a model that plots the whole curve. Okay, so you've got segments to that curve. You've got the baseline before the transit, then you've got the ramp down when the light starts to dim. When the planet is going from outside the limb of the star into the inside of the star, right? So now it's in front of the star completely. So now it's dipped down. You'll have a little bit more dip because of people are familiar with limb darkening for stars. So you've got a little bit of a change also because of the limb of the star. But overall, it's basically flat across the bottom, and so that's when the planet is in front of the star, when you have that flat spot. And then when it starts to egress, it's just like the Venus transit. Basically, you've got an ingress and egress period. It's a ramp. So we try to model every portion of this light curve to calculate certain parameters about the planet and versus in relation to the star.
I was going to ask you. So generally, how long does it take a planet to go in front of the star? I know it depends on the distance between the star and the planet, but what are the averages that you're usually looking at?
Yeah, so typical. Let's talk about these hot Jupiter type of exoplanets that are typically around the same size as Jupiter, maybe a little larger, maybe a little less, and they're really close. And these planets revolve around their star in like 3 days. Let's say 2.5 to 4 days.
Okay.
And that's like their year. Okay.
Mm-hmm.
A 3-day year. So they're whipping around this star pretty often. And then the time it takes to pass in front of the star is around, the ones we've done can be from like an hour and a half, 2 hours to 3 hours. So it takes that long to pass this. So this total session, if you want to get like an hour before the ingress and an hour after the ingress, can be from 4 to 6 hours for the total time.
Okay.
Okay. So that's pretty much a lot of the ones that are the easiest exoplanets to measure, and the ones that we're talking about those are the ones that have been detected because of the cadence and the amount of time that have been spent discovering these exoplanets. We haven't had we don't have any observations where we've stared at a star for a year to see if there's a planet that takes a year to go around, right? Or even 6 months to go around. So that's the problem with these with detecting these long-term periods for exoplanets. And it's much easier. You can do, over a 30-day period like what TESS is doing, you can detect, you might have 5 or 10 transits during that period to get some good data, where if you only have 28 days, you may see it once.
Yes.
Days is a longer than the 28 days.
So the exoplanets that you've been working on, these are ones that have already been discovered, or you as test subjects, and then you're using them to find unknown ones?
No. So one of the limitations, with amateur equipment is tough nowadays to do any kind of discovery. That requires these big, expensive instruments that the professionals use in space-based instruments. Because it's like a random thing. It's like winning the lottery. If you were to take a random star and say, I wonder if there's an exoplanet here, and you just observe it, you focus on that for 6 months. Let's say every night that's clear, you focus on it, and you're doing that one star for 6 months. And you've done let's say you've done 40 observation sessions with it. It's a crapshoot whether you're going to detect an exoplanet. First of all, it's because of the geometry of the system. So to help you understand, the transits, the planet has to pass in front of the star, which means it's a very small angle. It's got to be dead on pointing at us. Yes. And basically it's like 2% of the stars. Let's say there's planets around 100% of the stars, which they pretty much know. That due to that little inclination angle, there's only like a 2 or 3% chance for us to see any of the stars with the transit method. Okay. Typically they detect that stuff with the Doppler shift or using a spectroscopy method to detect these Doppler shifts, which does depend on a line of sight type of measurement, like what the transit method does. So first of all, we start out with a 2% chance that there's a transit that we can observe. Okay, yep. Then you have to observe it, however many times, because you don't know what the period is. Well, let's say it's a 3-day period. You've got a star that you're just going to pick and say, I'm going to look at this star. That means you have to accumulate a total session time of at least 3 days, if not probably twice that, to be able to even determine that it has an exoplanet if you're lucky. So it's possible, but I think we tried to calculate how much time it would be possible, how much time you would have to spend on a specific set of stars to discover, and it came out to be 6 months to a year's worth of observations dedicated to that. So in that regard, it's possible, of course, just like discovering a comet's possible.
Yes.
But it's very serendipitous, you know.
So most amateur work then is more related to observing known
or suspected exoplanets.
Known or suspected. Okay.
Right.
Especially suspected, because
that's right.
Tess gets one observation and discovers it. It's probably going to repeat, but
it's a candidate now. So I don't know if people are familiar with the TESS mission, but the camera system on the TESS satellite has got a very large pixel. Okay. Mm-hmm. Or I should say, the pixel covers a very large area of the sky because it's a wide-angle view. It's trying to cover an all-sky survey, so you're limited to the number of pixels, which means these pixels going to cover a large area of the sky, and we're talking 21 arc seconds on the side. So compare that to the standard amateur astrophotography setup, which is 2 arc seconds or 1 arc second per pixel. Mm-hmm. So what happens when TESS observes a field? 1 pixel may cover several stars, right?
Yes.
So you don't know so if you let's say TESS discovers this light dip, you don't know if it's because one of the stars is a binary star. You don't know if it's because one of them is an exoplanet. You don't have any idea what it is. So that's the purpose of the follow-up work is on the ground.
Gotcha.
It's to determine that, is to screen that out. So basically what TESS does is it creates targets of interest. Candidates, that's right. It creates these candidates that need to have follow-up work done on the ground to screen them out for false positives. Mm-hmm. And that's a big part of this follow-up work that we're going to be doing at the MSRO.
Cool. Now, when you're doing follow-ups, you're doing so without knowing the timing, right? So it's kind of like almost picking a random star and checking it, except you've got a clue that the star probably has an exoplanet. So you're when you're actually observing it, it's still a little bit on the random side of when the planet's going to go in front of the star, though, right?
Right. So TESS is the TESS will have probably several observations of this particular pixel, I should say, and that may be able to give them an idea that the period could be 3 days, 3.2 days, whatever it is. It'd say, I've got a repetitive dip in this pixel. Mm-hmm. Okay, so that's a candidate. That's all you can say, is that looks like we've got a repetitive dip, but we also have random dips in this pixel. It's hard, it looks like it could be a good candidate. So at that point, you've got a first value for a period. So now you can start to say, okay, based on this, it might occur again at this time, and then they create an ephemeris to tell you when the dip should occur. But it's only accurate to, it could be only accurate to an hour or so. Okay. So that means you have to have a long session around that time period to see, does it actually occur here? And then you got to measure each star within this. It's basically, we try to measure it within a 2.5 degree or 2.5 arc minute area, a circular area, where we compare all the stars at that location and see which one is actually causing the dip during that time period. Hopefully we got the correct time so that now we will see the dip and which star made the dip.
Question to the chat room here. It says small. Let's see, what would be the faintest star that you can do observations like this with?
All right, so of course it depends on the aperture of your telescope, but the telescopes we use at the MSRO, one's a 6.5-inch refractor, which we have the diffuser on, and then we also have a 12-inch Meade LX200 that we use. But the testing we did with the refractor, with the 6.5-inch refractors, we were able to do accurate measurements of a almost 11th magnitude star.
Oh wow!
So that's yeah. So the neat thing about TESS, and the reason they want ground-based follow-up work, is because TESS is focused on the brighter and closer stars, which are pretty interesting. So that's again, that helps our cause as an amateur to be able to observe these stars because they're brighter, which means we can effectively image the stars with smaller apertures and do these measurements. And then it also makes it easier to do this precise measurement because you've got a lot of photons to collect in a short period of time. So that helps.
Mm-hmm. I was going to say, amateurs participating in programs like this, where do they start, get into it, turn their observations into, things like that?
So if you search on Google the Test Follow-Up Observing Program, it's also called TFOP, T-F-O-P, Test Follow-Up Observing Program. You'll find the MIT website for the program. You may also find the NASA website that talks about it. But that's the gateway into this specific program. Kepler also has a follow-up observing program, and you can search for that also. But there's a lot of information for exoplanet follow-up programs in general. NASA has a big database called ExoFOP, for exoplanet follow-up program. Mm-hmm. And that's for all the different missions and different things to do follow-up work that amateurs can get involved with.
Kind of got a question here. Let's see, about the ratio of starlight during a transit. It'd be like, what if Jupiter went in front of our sun? Would that be about a 1% decrease?
That's correct. Yep, it's about 1%, and it's a geometrical calculation. So you're basically comparing the area of Jupiter as a circle compared to the area of the sun, right?
Yep.
So it's basic geometry. It's pretty simple to calculate.
And of course, it's always calculated from infinity, not from closer in.
Right.
Yes.
Right.
I was going to say, kind of a way of doing something similar to this, just visually, would be watching the moons of Jupiter go in front of Jupiter.
Exactly.
Which is quite an easy thing. So try to imagine like Jupiter being a star and the moon's being a planet. You can actually see the moon go in front of Jupiter. So kind of a similar thing that basically anybody could do with a fairly small, moderate-sized telescope, doing it visually. So just if you kind of wanted an idea of how something like this would look.
Yeah, that'd be an interesting experiment to measure Jupiter, the brightness of Jupiter, and then watch it as one of the moon's transits, and see if you can detect that light change. But I don't know what the ratio. I don't know how the moons are pretty darn small compared to Jupiter. Of course, it could be. But I don't know if there's be a 1% or less than 1% dip.
I don't know. You could definitely see the diameter of a moon in front of Jupiter, though.
That's true. And the other thing that impacts that is, of course, the shadow.
Yes.
Look like that'd be kind of cool to watch the shadow cross also.
Mm-hmm. That's definitely pretty easy to do. Actually, shadows are a little easier to see going across Jupiter because of the contrast.
Right. Mm-hmm.
And the moons are kind of the thing too. It's like if a bright moon goes in front of a dark band, look more contrast. Or if a dark moon goes in front of a bright moon, more contrast. But a bright moon in front of a bright band, you don't see it so much. And the dark moon in front of a dark band, you don't see it so much.
I guess that's the biggest difference is you don't have the sun is shining light on the face of the moon, and so that kind of distorts the light change.
Yes.
Exactly. And it's not like you're looking at in shadow.
Yeah. So you're not. It'd be more. I think more accurate would be measuring the shadow going across because that's always a light dip.
That's right.
Compared to a moon, a bright moon in front of a darker part of Jupiter. So. But then you'd have to figure out a way of collecting the total light of Jupiter combined together.
Mm-hmm.
That'd be interesting too.
Yeah.
Shrink it down to some really small magnification.
Now, the other interesting thing about Jupiter is it's already similar to a diffused image where it's a blob. It's not a point source, right?
Yep. Yes.
It's already a disk. It's already a disk.
Yes. Something else I was going to go, and I lost it now. Oh, well, I can't remember. I lost it. I was going to have you another input to that or a question or something like that, and kind of lost it. We got 5 more minutes, though. So let's see, what haven't we covered yet?
I think if you want to know more about this, my paper, you got the link there. I think, did I send you the link for the talk, for the presentation for the talk I gave at the imaging conference? I
can't remember.
I can send that to you.
Okay, sounds good. I think I have the link, in an email.
Okay.
I have to go double check because you did mention that in the email for us. So, project. What other projects were you working on? I remember my question. So I remember my question. So let's say you have to, when you're imaging a star like this, you have to have it be separated from other stars that could be too close, right?
Right. So when you so with a diffuser especially, you've got overlap in the stars. Okay, when you diffuse it out big, that is an issue that you don't have when you defocus. Typically, you don't spread the light out as much as you would diffuse it out to get more photons. But again, that goes to the assumption of your comparison stars. I don't know if it's a valid 100%, but you can typically assume that any of these dimmer stars that are next to the target star, if it's dimmer, then it's probably constant. It's not going to change. But again, that's similar to what the screening process with tests is. You cannot always assume that these stars are constant. So you got to be careful of that for sure. Depending on what field you're looking at. If it's in the Milky Way, then it gets to be difficult. If it's outside the Milky Way, then it's a little easier. That's much easier because you're not spreading the light out so much. But typically, the ones I've looked at, the few that I've measured, it hasn't been a big deal for the overlap. But it is an issue.
Do you use your cameras at prime focus, or do you kind of zoom in on them?
No, these are prime focus. This is standard. We use QHY cameras. We've got 174, which is a nice science camera. It's a 2 megapixel, and we also use a 16 megapixel camera that's on the main instrument to get a wider field of view. And we use that with a filter wheel with the diffuser in it.
Okay, so you're definitely looking at a wider field of view, and you could have several stars, and you have to make sure they're separated out so your diffuser can separate them.
Right. So that's one of the key things is to balance the size of the diffused image. There's different sizes of diffusers that you can buy based on the divergence angle, and because you have a fixed distance between the filter wheel and the CCD, the only control you have over the size of the profile is the divergence angle. So you don't want to diverge it. You don't want to diffuse the image out so far that you diffuse the stars out. You don't have very many to pick from a field, but you want to make it. But you don't want to make it too focused or too small to where you're not getting an effective number of photons collected in a certain period of time. Right. So you have to balance those two needs, right? So you need to have enough for comparison, and you need to have enough photons. So that's the balance.
All right. Well, we've come to the end of our show. Jerry, I really want to thank you for joining in tonight. Appreciate that. Glad you're here.
Thanks.
We'll get you back anytime you're ready to come back again. Just let me know. We'll bring you back. I want to thank everybody in our chat room tonight. Appreciate you all being around here, sticking around. That's still here. Glenn, Plaid Joan, Twist Edge, Aquafew, Plaid Mac, Optronics, SMCD, Plant Sisters. Yes, our whole family has been here. Because when you're in our chat room, you're part of our Space Pirate crew. Arr. All right, everybody. Time for us to head on out. Got more programming to listen to, so stick around if you like to. Good night, everybody. Thanks, Jerry. Good night.
I think. Arr.
We hope that you've enjoyed this program from AFM Radio, the broadcast service of Astronomy.fm. This program has been released under Creative Commons license. Please contact us for details. You may find more of our AFM original programs on our website. It's really easy to find us. We are Astronomy.fm. You may also find us in the iTunes radio listings near the top of the News Talk section, and also as an iTunes podcast selection. We'd love to hear your comments. Please email us at radio@astronomy.fm. Thanks so much for being part of the voice of astronomy around the world and across the known universe. This is Astronomy.fm Radio.
AFM.